Hello, my name is Ayşem Değerli. I'm a doctoral researcher at Tampere University. In this video, I will present reliable COVID-19 detection using chest X-ray images. The co-authors of the paper are Mete Ağısalı, who is also a doctoral researcher at Tampere University, and our supervisors are Professor Serkan Kiranyas and Professor Mosef Kabuş. Also, Dr. Muhammed Chowdhury is our collaborator from Qatar University. Coronavirus disease 2019 is caused by SARS coronavirus 2, which affects seriously people in high-risk groups and especially the elderly. The disease can lead to intubation, hospitalization, and even death. The disease is highly infectious, which brings many challenges to the healthcare systems, especially its mutations are even more contagious, making it harder to track and locate. Therefore, accurate and fast detection of COVID-19 has the utmost importance to prevent the spread of the disease. However, the diagnosis is challenging due to its similar symptoms with other viral infections. There are several diagnostic tools to detect COVID-19. One of them is nucleic acid detection with real-time polymerase chain reaction, which is also known as PCR test. There is also computed tomography to monitor the patient's lungs, and also chest X-ray imaging. The PCR test has high false alarm rate and is slow. On the other hand, CT imaging is expensive and it causes more radiation exposure compared to chest X-ray imaging. However, chest X-ray imaging is fast and it has the easiest accessibility. Therefore, in this study, we used chest X-ray images to detect COVID-19 from. In the literature, many studies have used deep learning models for detecting COVID-19 from chest X-rays, especially by transfer learning. However, these studies have many limitations. One of them is data scarcity. It's known that deep learning models need a lot of data to generalize the problem from. However, these studies have used very limited data set for detecting COVID-19. That's why it causes overfitting issue. On the other hand, they have used also control group that are formed by healthy subjects only or limited pneumonia types that can cause unreliability issue in the real life case scenarios. Uh, Additionally, there is a reliability issue of the deep learning models. When we check their decisions, they are normally from irrelevant areas on the chest X-rays that are from text, background, or bone areas. However, this has to be from the lung areas. That's why there is a reliability issue in the deep learning models. And lastly, the data sets should include early COVID-19 cases. These are the most important cases because it's very hard to discriminate early COVID-19 cases from healthy subjects, and it has the utmost importance in the prevention of the spread of the disease. So in our study, we overcome the limitations of the previous studies by proposing the largest COVID-19 detection dataset that includes also healthy subjects and 14 different lung disease types. And we also overcome the reliability issue by proposing an end-to-end network solution for that. And also our dataset includes early COVID-19 cases. So previous studies have proposed two-stage COVID-19 detection for a reliable diagnosis. For that, in their first stage, they form a segmentation network to learn the lung areas on the input chest X-rays. At the second stage, input chest X-ray is merged with the output of the segmentation network to form the segmented input chest X-ray. This image only includes the lung areas of the input chest X-ray and is used to train the classification network to diagnose COVID-19. By this approach, the network is forced to learn COVID-19 from the lung areas only. However, this approach is computationally expensive since two networks are utilized at the inference. Therefore, we propose an end-to-end network solution in order to overcome the limitations of this approach. In this study, we propose a reliable COVID-19 detection network, which is a ReCovNet model. In the training phase 1, we form a segmentation model that consists of encoder and decoder parts. For the encoder part, any state-of-the-art deep learning model can be used. For the segmentation model, we used a structure similar to the UNet model. So in the UNet model, the low-level features at the encoder part are concatenated with the high-level features at the decoder level. However, in our network, we have removed that by excluding the skipping connections. We have done that because we want to avoid the contributions coming from the initial layers. Therefore, the network can make decisions from the high-level features that are closer to the segmentation mapping of the network. By the observations, we have seen that this improves the reliability of the ReCovNet model. So after forming our segmentation network, we train it in the training phase 1, and we transfer its encoder weights to form the ReCovNet model. The ReCovNet model is formed after concatenating a global average pooling and fully connected layer after the encoder part. So in the training phase 2, we train the ReCovNet model. So this is the final network that is used for detecting COVID-19. So in this study, we have used two different versions of ReCovNet model that are version 1 and version 2. The difference of these versions are their encoder parts. Version 1 has DenseNet 121 and version 2 has ResNet 50 for their encoder parts. The major contribution of this study is the COVID-19 dataset that is the largest chest X-ray for COVID-19 detection. This dataset includes around 4,600 COVID-19 positive cases and around 120,000 control group chest X-rays. This dataset also includes around 1,000 of early COVID-19 cases that show no or limited sign of COVID-19 pneumonia. The control group checks X-rays in this study are from healthy subjects and from 14 different lung diseases. The dataset is publicly shared to the research community. You can easily access it by scanning the QR code here at the top corner, where you can access our dataset and check our project website. Here we compare the COVID-19 stages with the healthy subjects. You can see that when the COVID-19 is at its severe stage, the pneumonia is visible on the lungs, and it's very easy to discriminate it from a healthy subject. On the other hand, when the COVID-19 is at its early stages, like limited infection or no infection stage, it's very hard to discriminate it from a healthy subject. This makes the diagnosis even more challenging. And for the control group checks X-rays, we have 14 different types of diseases. In the data processing part, we have resized all the checks X-rays to 224 to 224 pixels. Then we split the dataset into train and test splits based on the checks X-ray 14 dataset train and test ratio. It was already predefined, so that's why we have used the same ratio for the other images coming from different datasets. And also we have augmented the data by 10% randomly shifting it to the horizontally and vertically. And we have also randomly rotate images in a 10-degree range. Here you can see the details of the dataset. There is the test samples, and after augmentation, these are the numbers of training samples. In the experimental evaluations, we first evaluated the training phase 1, where we trained the segmentation networks. A dataset consisting of 385 check X-rays is used for this task, with their corresponding ground truth segmentation masks. The dataset is split into training and test sets with a ratio of 80% to 20%. Then the training set is augmented up to 1,000 samples. Using the trained set, the model is trained over 15 epochs with a learning rate of 10 to minus 4 and a batch size of 32. The table shows the segmentation performance results over the test set, and the two encoders are used for this. segmentation network because we use two versions of the ReCovNet model. As you can see from the table, the sensitivity and specificity levels for segmenting the lungs on the chest X-rays are high. Here we evaluate the ReCovNet model in the training phase 2. The model is trained over 15 epochs with a learning rate of 10 to minus 5 and a batch size of 64. In the table, you can see the detection performance results of the state-of-the-art and the proposed ReCovNet model over the tested of COVID-19 dataset. Here you can see from the table that ReCovNet version 2 has achieved the highest sensitivity compared to other models, and it also has achieved a very high specificity level as well. Compared to that, from state-of-the-art deep models, the DenseNet 121 has achieved the highest specificity level, which is very close to the ReCovNet version 2. However, now we will check their activation maps to see their reliability, and we will compare them. Here you can see the confusion matrices of the two best performing models from state-of-the-art DenseNet 121 and from the proposed ReCovNet version 2 models. As you can see from the confusion matrices, ReCovNet model have correctly detected more COVID-19 cases. From the figure, we can see the activation maps of the proposed and the state-of-the-art models that are produced from gradient-weighted class activation mapping GradCam method. The top two rows are from COVID-19 samples and the bottom row is from control group. As you can see that the chest X-ray images are correctly detected for these cases, and for the ReCovNet model, the decisions are from the lung areas only. That makes them reliable for COVID-19 detection. And also for the state-of-the-art models, you can see that the decisions are coming from background, bones, or text areas, which are irrelevant decisions for us. That's why state-of-the-art models are unreliable for the COVID-19 detection. In conclusion, we can say that automatic and accurate detection of COVID-19 is a crucial task in order to prevent further spread of the disease. In this study, we have proposed end-to-end reliable COVID-19 detection network that has achieved superior performance over the state-of-the-art deep models. And also in this study, we have overcome the data scarcity issue by proposing the largest data set, which is COVID-19, for the purpose of COVID-19 detection. In this study, we have checked the reliability of ReCovNet and state-of-the-art deep models by the activation maps approach. And also for the future, we want to include more chest X-rays in the training phase 1, where we train the segmentation models in order to further increase the reliability of ReCovNet models in the COVID-19 detection. So you can see the QR code where you can access the project website, and thank you for listening.